Hi, welcome to the third and final unit of our finance, short unit on finance. We're talking about ordinary annuities. So we're talking about what actually an annuity is today. Um, so learning goal is to make connections between geometric series and an ordinary annuity. And a couple things that you're going to need to be able to do is create a timeline in a series, calculate regular payment for future value or present value, calculate total interest paid, and describe the effects if you change conditions using a TVM solver. And we're not going to get too far into this. We're just really going to look at using the TVM solver and then seeing how easy you can make calculation changes. So warm up here to just challenge you to kind of think about how much money would you have at the end of 4 months. So uh, based on versus the last lesson, we only had one payment. So we had $100 maybe at the beginning, and then we want to find out what it's worth at the end. Here you actually have four payments, so four investments. Um, so what we do is we take the interest rate divided by 12 because it's compounded monthly. We got to find out the monthly rate. Um, Consider the 100 in there for 3 months. So it's 1.0025. It's growing by that factor 3 times. The second one's only in there for 2 months. The second last one's in there for 1 month. And the last one actually just got there. It's only $100. And if you add those up, that's actually how much money you would have. And then ask yourself, like, what do you notice about that calculation versus Unit 5, where we talked about geometric series? So an annuity is a series of equal deposits or payments made at equal time intervals. So at the end of every month or something like that. Um, an ordinary annuity is when it's the payments are at the end of every month, and then a simple annuity is when the payments coincide with the compounding rate. That won't always happen, but in this course, that's the ones we study, where you have something like compounded monthly and then monthly payments. Um, so you deposit $1,000 at the end of each year, 5% compounded annually. We're going to look at drawing a timeline in a series. So if the interest rate is 0.05, the N is 5, it's 5 payments. So we just write it like a little, really a number line from 0 to 5. The payments are at the end of every year, so they're on the top after every year is over. And then each time, so that's the timeline. Then the series is just actually taking those payments to the end. So the first one would be in there for 4 years, very similar to the warm up. The second one's in there for 3, 2, and then 1, and then the last one just got there. And that's actually what we call a geometric series. So we can add those up with the geometric series formula if you'd like. And notice that you're going to expect more than $5,000. $5,000 is how much money you'd have. What this grows to, the sum of this series is actually the amount over 5,000 is the interest earned. Looking at a future value question, so similar, $500 at the end of each quarter, compounded quarterly. So the timeline is 40 quarters in 10 years, and the $500 is the end of each quarter. This is one where you don't actually have to like write every one. You just kind of put a dot, dot, dot. What's important is that you see the first couple and the last couple. That's the timeline. And then series, if we want to find out what it's worth at the end, we're actually going to just kind of write it the first one first. So the other ones we wrote the last one, or this one first. We're going to write the last one first. So $500 is the first one. The second one is in there for 1% because it's 4% per year. And then, so it's $500 times 1.01 to the 1. This n value is only for the sum. So this coincides with the 40 terms, but it doesn't coincide with each individual term. Each individual exponent is going to be a different value depending on how long it's in there. And then the last one's in there for 39 quarters. That's actually what we know is a geometric series. It's 40 terms, starts at 500. The A value is 500, the R value is 1.01. Plugging them into the sum formula with N is 40 is the 40 terms. It looks like this. And then it adds up to 24,443. So question is like how much interest was made. If you multiplied 500 by 40, you'd get $20,000. 4,443 is interest. That's not a hard calculation. You just have to multiply the payments by the number of periods, and then just subtract. So this is the compound. This is the compound future value formula. So this is kind of like the geometric series formula when we add them all up. This is the big formula. It means add up a whole bunch of little compound interest investments, individual ones at regular intervals. Those are the regular payments, but this will add up all of them. Similarly, we can do this for present value. So if you owe money, you owe money now at a monthly payment of $300. You want to find out how much money you owe. The $300 goes at the end of every month. You're going to do it for 60 months because it's 5 years. The interest rate is 3% per year, but divided by 12 is 0.25% per month. The geometric series, starting with the first term. This time we're not taking them to the future, we're actually bringing them back. So we can actually bring $300 back one, or divide by 1.0025 to move it to 0, the present. 300, 1.0025 to the negative 2, to the negative 59, and to the negative 60. If we wanted to add those up, it's actually a lot messier than the future value formula. The A value is not so nice, that's the first value. The R value is not so nice, it's 1 over 1.0025, or 1.0025 to the negative 1. The N value is 60, and when you sub it in, it kind of looks ugly. But it does give you the present value. So if you multiplied 300 by 60, you'd get $18,000. That's how much you're going to pay for this loan. The present value is $16,695. This is the formula for present value. So a little bit nicer than this. The formula for present value gets algebraically rearranged, and you can, as a challenge, you can try to do that yourself. And it's used for loans or income funds where you invest a certain amount of money, and then you want to like collect off that money. So you can imagine you run into a bunch of money, like sell a house or win the lottery. You put it in the bank, and you can actually live off that money. So it's present value though. From previous example, we can see this formula versus this formula, and you can see how the calculation is a lot nicer looking, but it gets you the same answer. So again, if you wanted to algebraically prove that those are the same, you could. And I could challenge you to do that, but it does get you the same answer. This present value formula is a lot nicer. Example, so compounded monthly, so how much money will you have? And so that's kind of looking at a future amount, so how much you're going to have in the future. The interest rate's about 1/3% per month, so it's 0.04 divided by 12. We do a lot of monthly examples. This could be quarterly too, but with monthly, you divide by 12. We're going to do it for 48 months. Timeline looks like this, 48 months and then $100 each time. Kind of writing them all out, taking them to the future. We got the 47. The first one's in there for 47 months. The second one's in there for 46. The second last one's in there for 1, and the last one just got there. So that's actually like the timeline and the series. And then you can plug them into the future value formula, and you get $5,195. You can compare that to 4,800, which is 48 times 100, and it makes sense. Like you paid $4,800 and you have $5,195 in the bank. Now we got a purchase price of the car, so the present value or future value. You can ask like, what is the purchase price of the car? So what is it now? So we're doing 8% per month, so or per year, so it's 8% divided by 12. 36 months here, so you can get your 36 payments of 400. Bring them all back to the present, so divide each of them by 1.0066. And the second last one's 35 times, and the last one's 36. Plug them into the present value formula. Make sure you can do this calculation on your own. You're comfortable with it. You get 12,000. And compare that to 400 times 36. Um, if you multiply 400 by 36, you'll notice that you actually end up paying more than the purchase price of the car because you're borrowing money for it. Final one, 17,000 OSAP loans. So we're actually not doing a timeline, a series here. We're just kind of writing out what we know. We know the present value is 17,000. The interest rate's 8%, 8.5% divided by 12. We're doing it for 24 months. Sub everything into the formula, and we're looking for R. So you can do this calculation first. You get 21.9995, and then divide 17,000 by that, and you get the monthly payment. If you multiply that by 24, you'll notice that she ends up paying more than $17,000. Looking at the TVM Solver now. This is the app, the website that you can get on Android or iPhone, or you can go to this website and it works really nicely. It's what you're looking for is the TVM calculator. Just a couple things about the app that you need to know. Again, the present value payment or future value, one of those has to be negative because there is direction of payments happening, and so one of those will have to be negative. The annual rate, we actually don't divide at all. Just take the rate that's given in the question, the rate per year. You don't even divide by 100. The periods, you do have to figure out how many periods it is. So if you're doing $10,000 your present value, you get 2% annually. You're going to plug in 10,000 as your present value, sub in 2 and 12 for the number of years. Do drop down annually, and you click this button here for payment, and it gives you negative 945. The payment's 945. It's just saying that it goes in the opposite direction. The next one is written kind of funny, but the future values of $300 at the end of each quarter is 14,000. So the future value is 14,000. The payment's 300. We're looking for the number of years. We can plug in 8, but you have to plug in either future value or payment as negative. So if you plug in negative 300, 14,833.29. If you don't plug a 300 in here, you might get a negative number here, and that doesn't make sense. You should never get a rate of negative or periods of negative. We drop down quarterly. Now that's the number of quarters. It doesn't take 33 years at $300 per quarter. It takes 33 quarters. If you divide that by 4, you get 8.3 years. So that's one step you have to do. If you're looking for the number of years, you've got to kind of just think about it and figure out how to get it to years. $300 at the end of each month for 3 years is, again, 14,000, but this is now it's monthly. So you plug in 300 as your payment, 14,000 as your future value. So you can plug in negative as the 300. Periods is going to be 3 years times 12, which is 36. And the annual rate's what you're looking for. Make sure you've got monthly there. And the annual rate is just 17.17% per month. This kind of explains why they do annual rate, not like asking you to divide it, because it's what's simplest to come out. And there's some practice.